we've talked about the mathematics of translating between a binary number and a decimal number, and how to represent decimal numbers with digits, floating point numbers, as binary numbers. And that's all good, and that's math. But that now leads us to one of the most exciting capabilities of the Arduino, and one of the primary ways that these embedded systems can interact with the real world. And that's called analog to digital conversion. Analog here means some number in the real world. It is 72.6498 degrees Fahrenheit in this room. There's a certain amount of solar flux or wind or sound. Those are represented by floating point numbers. And I want to get that into the computer and into maybe a floating point or an integer representation so I can work on it. And it turns out your Arduino has circuits that do this A to D, analog to digital conversion. It doesn't have the other way, digital to analog. But we need to understand that. We really need to understand it because everything we've been talking about, plus a couple other things, come in here. And if you don't understand how it's working, it's not going to work right for you. You're not going to be able to apply it. So the basic little black box function of an analog to digital converter, which I'll call a DC, sometimes it's a 2D is how people write it, but analog to digital converter, is we're going to take some voltage in. We're going to turn whatever sensor data that we get into a voltage, because that's typically how we represent values in a computer system. It's going to produce for us an integer number, n, and this may have m bits in it. And it's very important to know how many bits are in this integer number. It turns out there's two other inputs to this black box, if you'd like, so I'll draw them here. And this is V low and V high. This is going to bound the range that your input voltage can be. You're going to map this input voltage to this integer number such that when the integer number is 0, you're at V low, and when the integer number is the largest it can be, given the number of bits, you're at V high. So these are very important, and this is, you can adjust these, and you actually can adjust this on your Arduino. And you want to adjust this to be pretty tight around the range of input voltages you think, so you can use these bits best. And if that doesn't make sense, let's write it out. The Arduino command for this is this. Analog read, and only certain pins will do this, and they're marked on there. And here goes a pin number. So some voltage V in is connected to some pin. You execute this command, and you get this number n. But what does this number n mean in terms of what that voltage was? That's our question. How precisely does it measure that voltage? That's the kind of questions we want to ask. Let's imagine, because it'll make it a lot easier to draw, that we have an m equals 4-bit system, because that is, which you have lots more, but I can draw that. And that means n, what we get out, goes 0 to 15. That's the maximum it can be. Let's map our input voltage between 0 and 1. And what I mean by that is, I'm just going to make a line out of this. So slope-intercept, V high minus V low. So if V in is V low, I get 0. And if V in is V high, I get 1. So this represents my input voltage. And if my V in is outside of the bounds high to low, I'm off here in Never Never Land in bed. So what I want this function to do is that. That would be the ideal transduction between input voltage and digital signal integer inside the computer. And it almost does that, But there's a problem, is I only have 15, 16 values here. This is continuous, this is discrete. And so how this is going to work, let's see how I do this. There's 8, 4, oh yeah, this will work. So I'm making 16 tick marks here. If I did that right, 1, 2, 3, 4, 5, 6, 7, 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Awesome. So there's 16 ticks. If the input voltage is between 0 and 1/16, set by this scale, of my range of voltages, then what this function really returns, awesome place for color, is n equals 0. It has to. That's all I got to output. When my input voltages goes above 1/16 of the total scale, I get 1 out. When it goes above 2/16 of the total scale, I get 2 out, etc. So this really implements this function. And the last one would be here, and that would be, 15. And that's just the best it can do because my output is quantized. So the bit depth is what this is often referred to. Of this analog to digital converter was 4. And you can see it's going to be a fairly crude readout of your input voltage. The more bits you have, the more precisely your actual function goes to the ideal, which is that continuous line. This also implies that there's a finite error here, or uncertainty. If I look at this, in this case, this is 1/16 in our case of m equals 4 of the entire range. And the entire range, that's an equal sign, was V high to V low. So in general, what did I call this? Quantization error. The quantization error, QE, equals that total range you set up. You've defined this device to work. And I think in the Arduino you can't change V low, but I believe you can change V high, over 2 to the m, however many bits you have. And that's a voltage quantization error. That's your uncertainty in what your input voltage is because your output is an integer. And then the last thing to think about, which is now completely on the board, is if you use a certain pin on your Arduino and you attach to it a sensor that is going to provide a voltage, you read in your Arduino with this analog read command in your sketch, and you get a number. You can go look up what integer range you can get in your Arduino so you know this scale. You know how many bits are in this number. You want to take this integer and turn it back into the best approximation you can, given this quantization, of Vin. You have to run this process backwards. So that is a simple process of inverting this equation, which is the reason I've written it all down for you. That tells you how to take this integer that you get inside the computer, do some math in your sketch, and come out with Vin. Very likely, this sensor you're using, maybe a temperature sensor, has its own equation, ideally a line if life is good to you, which relates the temperature to the voltage that was on this pin. So you also need to write down that math so that in the end you can have a function which says read temperature, and it goes through all of this, reads this integer, does this operation, takes some integer that you get, turns it into some voltage, then having that voltage, which of course you need to know V low and V high to turn this into Vin, then it takes an equation for Vin and produces temperature and hands you back a temperature. That's the basics of analog to digital conversion and manipulation of your data that you read to turn it back into this approximation or estimate of what signal you really had out there in the real world.